Welcome to 4.5.
Radicals!
Radicals.
They're multiplying!
We're going to be multiplying radicals too. When we do so, we're going to have a couple of radicals, and they might be an entire form or a mixed form. But we can do that when we have radicals with the same index. When we do, we take the coefficients and we multiply them together to get the new coefficient. And we take the radicands and we multiply them together to get the new radicand. If you want to throw in a substep, you can throw in this part right here, but it is extremely unnecessary. So this little one-step multiplication, we think you could do pretty quickly, but if you need that middle step, that's cool and you can do it. But again, it's just the whole number components get multiplied to give you your whole, and then your radicands get multiplied to give you your new radicand. If you want, you can even give it a try right away with these first four examples. In IGO, I'm going to say that the whole part of this is 6 because that's 2 times 3. And then there's a radical part, and that's going to be 5 times 2 to give me 6 root 10. This one is, woo, done. On to the next. We've got 4 root 11 times 7 root 2. Our answer will be a mixed radical, where the whole number component is 4 times 7 to give us 28. And then 11 times 2 will tell us that our radicand is 22. Woo! We are on fire! Not literally, but figuratively, so let's just keep going. We've got 9 root 5 times 6 root 6. 9 times 6 is what gives us our whole number component. 9 times 6 is 54. And for our radical part, we have 5 times 6, because that's what's under the radical sign there. Those are our radicands. So 30. And the last one, look at me blaze a trail. 2 times 8 is 16. And we've got the root of something. That's 10 times 21 for 210. Excuse me a moment while I put boxes around all my answers, because boxes are great. Quadrilaterals are among my favorite laterals. And that's the intro of how to multiply two radical terms together.
Now, of course, as we do this, in these 4 examples, all of our radicands, or our radicals, could no longer be simplified. But that's not always the case. So after we do the multiplication, even though it's just a one-step multiplication, we're going to check to make sure that it can't be further simplified. And if it can, we're going to do it. So let's take a peek. Oops. So again, with multiplying radicals, we're just going to go whole number times whole number. So 2 times 5 is 10. And then radical times radical, or radicand times radicand. So 6 times 3, giving us 18. Now, taking a look at this, this is not fully simplified. Because if I'm looking at the radical, 18, this is the square root of 18 here. It has a factor that is a perfect square. So I can rewrite that as 10 times the square root of 9 times 2, which is equivalent to 10 times the square root of 9, which is 3, times the square root of 2, which is 30 root 2. Now, this is fully simplified because there's no factors of 2 that are perfect squares, so this is where I'm getting out my quadrilateral and moving on up. And by up, I mean across the page to the next example. And here again we go. If you can, and I know you can, pause this video and try this next example on your own. Oh, baby, we're back! 5 times 3 is 15. Root 2 times root 10 is root 20. Root 20 is not fully simplified. It can be expressed as root 4 times root 5. And of course, root 4 is 2. So 2 times 15 gives me 30. And I have 30 root 5. And root 5 cannot be simplified because it has no factors that are perfect squares. So I'm going to quadrilateral that as well.
We can also multiply radical expressions that have multiple terms. And we're going to be using the distributive property, just as when we had something like x times 2x plus 1, we would have to distribute that x to both terms. We can do same here. So in this little example, we've got 7 root 5, and it's being multiplied by root 10 plus 2 root 2. So we're going to distribute. We're going to take this 7 root 5 and multiply it by root 10, and we're going to multiply it by 2 root 2. So that's what this first step here shows. Now this line itself is not necessary for you to show, but it does for us indicate what's happening. So we're taking 7 root 5, we're multiplying it by root 10. That's this first distribution arc. And we're taking 7 root 5 and multiplying it by 2 root 2. That's this second arc for the distribution. What you do need to show is this line. So you do need to show that. And then from there, now that we've got that first little bit done, now we've got 7 times 1 is 7, and 5 times 10 is 50. Now we've got 7 times 2 is 14, and 5 times 2 is 10. Now that we've got that, we do need to simplify. We need to make sure all those radicals are in fully reduced form. So that's what we see here. We see this breaking up of the 50 into 25 and 2. The 10 can't be simplified, too bad, so sad. And then turning the root 25 into a 5. And of these steps, actually, yeah, you would need to show all of them. You need to show that, you need to show this. Of these ones, you could show one of these. Well, you have to show the last one anyways, is what I should say. Woo! There we go. Nailed it. And that's that. Ooh, I'm out of breath. I need water because of my out of breathness.
That makes sense. All right, so we're just going to go ahead and ignore Mr. A and do this example instead.
Sound like all my friends in elementary school. What?
Oh. Anyways, yeah, let's go. Why don't you pause, because I think we all need a moment here, and you can try this example on your own. And welcome back to this much happier note. So we are distributing this 4 root 2 to both of the terms inside my brackets. So 4 times 2 will give me 8. Root 2 times root 3 will give me root 6. My second distribution, 4 times 1, because remember there's a secret 1 there. 4 times 1 will give me 4, and root 2 times root 6 will give me root 12. All right, now I'm going to take a look at these terms and see if I can simplify them further. Since I'm dealing with square roots, I'm looking for factors of 6 and 12 that are perfect squares. 6 does not have any factors that are perfect squares, so it's going to just stay as such. It can't be further simplified. But if I'm looking at the root 12, I know that it has factors 4 times 3, in which 4 is a perfect square. So here I go, 8 root 6 stays same. But looking here, I have 4 times root 4, which is the equivalent of 2. So 4 times 2 will give me 8. And then I have root 3 left over. Now, I can't end up simplifying any of these because they don't have any like radicals. But I've done my best, I've tried, and I can now be certain that this is my final, most simplified answer. Taking a look at the next one, we have a double distribution here, so kind of like FOIL. I remember that. I do. So I'm going to start with distributing the 2 root 2 to both of these. Well, I really thought I could move to the side here. All right, I guess I'm working down. So 2 root 2 times root 5 will give us 2 root 10. 2 root 2 times 3 root 14 will give me 6 root 28. And I'm also going to be distributing this negative root 10 to both terms in the second bracket as well. I don't know, I'll stick with the green. So I end up with negative 1 times 1, which is negative 1. And then root 10 times root 5, which is root 50. And then negative root 10 times 3 root 14 will give me negative 3 root 140. Ay caramba. Okay. So, with this, great, the distribution's done, but now I'm going to go ahead and simplify. So taking a look at my first term here, 2 root 10, well, 10 doesn't have any factors that are perfect squares because I'm dealing with square roots, so she done. Next one, 28. The factor that's a perfect squared is 4, so I have 4 times 7, so that's 8. Continuing on here, root 50. Ooh, I could rewrite that as root 25 and root 2. And the last one, oh, let's see here. I know that 4 goes into 140, and 4 goes into 140 if it's 2 times 70, then 4 times 35. And there we go. And now I can rewrite the ones that don't change. Okay, just the first one here. And simplify further the next one. So 6 times 2 is 12, so I have 12 root 7. Then I have negative 1 times 5, so negative 5 root 2. And negative 3 times 2. Ay, ay, ay. Baby, come back. Ay, ay. Whew. A moment of fright there.
Yeah, it was scary.
Okay, negative 3 times 2 gives us negative 6 root 35. And it looks like there's nothing to collect there, but I know that I've done my due diligence. I've simplified everything as best as possible, and now I can move on
to this one, where we're going to perform that FOIL again, that double distribution. I'm going to draw my arrows one at a time here. So 5 root 3 times 5 root 3 will give me 25 root 9. And then I've got 5 root 3 times negative root 7, which gives me negative 5 root 21. Now I've got to take root 7 and multiply it by 5 root 3, which gives me positive 5 root 21. And then root 7 times negative root 7 is negative root 49. Interestingly enough, for this example, some of these simplify quite neatly. 25 root 9 is 25 times 3. And then we're going to lose 5 root 21s. We're going to regain 5 root 21s. And then root of 49 is 7. And you might notice that these are same, so when they collect, that's just 0. Our next line, we can say we have 25 times 3, which is 75. And this is all eliminated, so we just have that negative 7 at the end. And that gives us a final answer of just straight up 68. Oh, that's funny. Our initial business had radicals involved, but our final answer is just a nice rational number. Well, I won't stew about it. I'll go over here. And again, distributing. 4 root 3 times root 6 gives me 4 root 18. 4 root 3 times negative root 3 gives me negative 4 root 9. We've also got 1 times root 6, which is just root 6. And we've got 1 times negative root 3, which is negative root 3. Simplifying these as best I can, I see that the root 18 is just like root 9 times root 2. I'll just keep this as 4 times, well sure, let's call it 4 times 3. Root 6 can't be reduced at all. Root 3 can't be reduced at all. 4 times root 9 is the same as 4 times 3, which is 12. The root 2 we couldn't do anything with. 4 times 3 is again still 12, so that's there. Root 6 was just root 6, and negative root 3 was just negative root 3. So they didn't have anything to combine with, but that's okay. They'll find their way.
All right. We've got 2 examples left, and we are going to continue on with this double distribution. So we're going to distribute the 5 root 5 to both terms. So our first term becomes 5 root 75. Our second distribution here becomes 5 root 15. Our first distribution of our second term becomes negative 6 root 15. And our second distribution of our second term, that's a word, mouthful, it is a mouthful, is negative 6 root 3. Beauty. Now, right away, I can see that these guys are going to collect. I personally I'm going to collect them right away just because I don't want to have to write them out twice every single line and then collect them at the bottom. I'm not lazy, I'm efficient. But as I do that, I'm also going to start trying to simplify my other terms. So if I'm looking at 5 root 75 because it's a square root, I'm looking for a factor that's a perfect square. And so I'm thinking of root 25 and root 3. Looking at our next two terms, they both have root 15 in there. Looking at 15 as a radical, or as just a number, there is no factor of 15 that is a perfect square. So I'm just going to go ahead and collect them. So 5 minus 6 will be negative 1. I don't write the negative 1, so I'm just going to write negative root 15. And then I have my minus 6 root 3. And again, root 3 can't be simplified because there's no factors of 3 that are perfect squares. Oh, that's nice. Now, taking a look at these guy over here, we have 5 times root 25, which is 5 times 5, which is 25, root 3, and everything else stays same. Oh, but what didn't you know? We have 25 root 3, we have negative 6 root 3, those can be combined. So we will end up with 19 root 3 minus root 15. What un beauty. Now, I don't know what you've been doing with your life, if you've been pausing, if you haven't. If you have not yet been pausing, because sometimes we forget to tell you, please make sure you pause now and try this last example on your own. I believe in you. So does Mr. A. He also said he believed in the dream. But here we have it. First distribution. We end up with 8 times 9, which is 72, and root 2 times root 5, which is root 10. Then, first distribution. My O from FOIL. We have 8 times 6, which is 48, and root 2 times root 10, which is root 20. My I from FOIL. We have negative 45, root 5. And my L from FOIL, we have negative 30 root 10. And just like in that last example, I can see right away that I have some terms that I'm going to combine. I like to combine right away if I can, because I don't like writing things down multiple times from line to line. So I'm going to go ahead and do that. 72 root 10 minus 30 root 10 will give me 42 root 10. 10 has no factors that are perfect squares because we are dealing with square roots here. So I cannot further simplify that term. But moving along, if I'm looking at 48 root 20, well, root 20 could be written as root 4 times root 5. And 45 root 5 cannot be simplified further because root 5 does not have any factors that are perfect squares. So going ahead and rewriting that first term, my second term here, because my root 4 is essentially the same thing as a 2. 48 times 2, well, that just gives me 96. I still, of course, have that root 5 minus 45 root 5. Oh, hello there. We have 2 root 5s. Well, actually, we have a 96 root 5 and a negative 45 root 5. And they're just hanging about. If only they could be collected. And they can actually be. So that's nice. So we end up with 51 root 5. Whew! That was actually a really great question. I'm really happy with it. I'm happy with how it turned out. I hope you also enjoyed it. Life's pretty good. Now, if you scroll/flip pages here, you'll notice that there's some practice work there.
Yes.
give that a try. There are some answers at the bottom, so you could also give those a look-see-poo after you're done. But otherwise, that is it. That is all.
Oh, I should note that I was educated after the end of last lesson as to the origin of Hasta la Pasta, and it is from a show that I've seen, so I should have recognized it. It is from Phineas and Ferb. It is said by Dr. Heinz Doofenshmirtz, the leader of Love Muffin, if you will. And he says Hasta la Pasta, and it was humorous in that moment, just as it was humorous when you said it, Tibbs. So I am hereby acknowledging that I should have recognized that, and I feel like a fool for having not recognized it. And on that note, I would like to say, hasta la pasta.
Hasta la pasta to you too.
Hasta la pasta, everyone.